So what we are discussing, so we try to find out the Green's functions. Basically, we are interested in finding a general representation formula for the PDE or the solutions of the PDE, which is minus Laplace u is equal to f in omega, where omega is an open set in Rn. Okay, it may not be bounded with C1 boundary. Okay, it may not be bounded with C1 boundary, and u is equal to g on del omega. So C1 boundary we are considering, and these things. Okay, so then what we have seen that now suppose u is a solution to this problem, then we end up with, and then we incorporated the fundamental solution phi. And then what we got from there, that u of x, which is integral over omega f of y, phi of y minus x d of y plus integral over dou omega, then dou u, dou nu, phi of y minus x minus g of y, dou phi dou nu of y minus x of d sigma y. This is the surface measure. So the problem here is that I need to find out the normal derivative dou u dou nu, okay, along my del omega, which is unknown. So this suggests me to consider a correction function, which I am defining. This is my correction function phi x of y. Okay, means x is fixed and I'm looking for y from my omega, such that it solves my boundary value problem. Laplace px of y is equal to 0. That means it is harmonic in omega, and px of y, this should be my p of y minus x. This is just looking at that on del omega on del omega. Okay, so we want to find pxy, the correction function, such that it is harmonic in omega and in the boundary. Oh, why it is not working? My iPad is not working. Okay, so what we want, that correction function phi xy I don't know why it's not working. Nice, okay. So the correction functions I want phi xy such that it is harmonic in omega, and then phi xy should be phi of y minus x, where my this phi is a fundamental solutions of Laplace equations in Rn. Okay, so what I can do it from here, that if you use the integration by parts formula again, because what I know that Laplace pxy is equal to 0. So if you use the Green's formula, then I can have integral over omega pxy Laplace of uy dy. Okay, because Laplace of px of y, that is actually is equal to 0. Laplace of px y is equal to 0 harmonic. So these things actually I can write down. This is integral over dou omega u times dou nu of px of y minus px y of dou u dou nu of y and then d sigma y. Is it not? This part I have. So now these things, what I can write down, this is integral over dou omega, because phi xy on den omega, it is my phi of y minus x. So this is nothing but u dou nu of pxy minus this one is phi of y minus x and dou u dou nu of y of d sigma y. Okay, so now if u is a solution to your Poisson problem, then I know that u is equal to g on the boundary, is it not? And Laplace minus Laplace uy, that is equal to f. So minus Laplace u is equal to f in omega, and u is equal to g on del omega. So from here, what I have, integral over omega px of y. Now this is fy dy. This thing is equal to integral over dou omega. This is now g times dou nu, g means g of y, dou nu of pxy minus phi of y minus x dou u dou nu of y of d sigma y. Okay, so now these equations I have, and then again I have my these equations. You see, I want to replace my this dou u dou nu phi of y minus x, that is actually I have from here. Okay, so now if you put the left hand side this part, and then you put right hand side, and then if you put this value, so this implies integral over dou omega phi of y minus x dou u dou nu of y d sigma y. This is nothing but integral over dou omega gy dou y of pxy minus integral over omega pxy of fy dy. Okay, so now if you replace this value in here in these equations, then what I have the following, that u of x, which is integral over omega f of y. Now I have phi of y minus x minus phi of xy of dy minus integral over dou omega g of y, and then I have dou nu of, again this exactly same part, phi of y minus x minus phi x of y d sigma y. Okay, so that means if u solves my Poisson equation, so we incorporate the fundamental solutions phi, and then what we end up with, that the solution ux has the following representation. So now looking at these expressions, we are defining so-called the Green's function. Definition: Green's function. So I am defining g of xy, which is my phi of y minus x minus phi x of y, where phi x of y satisfies your previous things. Okay, so this is harmonic in omega, and in the boundary it is phi of y minus x. These functions I am defining for x, y it is in omega, but x is not equal to y. Okay, so these functions g is called Green's functions. So as long as if you find out the Green's functions for omega, okay, this is Green's functions of the domain, okay, depending on your domain omega. But okay, how to find out the Green's functions? So that means my Green's function should satisfy these things, that phi of y minus x minus phi x of y, where phi xy, that means I need to find out my these correction functions phi xy, which satisfies the harmonicity, means it is harmonic in omega, and on the boundary it is phi of y minus x. Is it not on the boundary? So whether it's depending on the omega for each given domain, we cannot find out the Green's function. Okay, so by the way, what are the properties of your Green's functions? And whether if I this expression, then whether it satisfies, because I have deduced it under the assumption that, okay, suppose U is my solutions, then I have deduced in this part. So then we will try to look at, now suppose I have this kind of expressions using these Green's functions. So whenever I am looking at this Green's function, see that there is no solution for the problem or so on. No, it is just depending on the, because I have the fundamental problem and then I have satisfied these equations only, depending on the domain. And then I'm saying that if I just replace by here, so u of x is equal to integral over omega f of y, then say g of xy dy minus integral over omega g of y dou nu of g of xy d sigma y. Okay, then this expression u should satisfy your Poisson problem minus Laplace u is equal to f in omega and u is equal to g on del omega. Okay, and not only that, u is in also C2 of omega closure, which solves the Poisson problem, and it has a expression in this form. Okay, so that means it boils down to find out whether we can find out Green's functions or not for that domain omega. Okay, but what are the properties of Green's function? So it has a nice property. In particular, if you look at the Laplace of that Green's function with respect to x or with respect to y, this is actually 0. So phi of gxy is equal to 0, and then Laplace x of g of xy. And not only that, it is symmetric about, okay, so always this is x, y is in my omega, but x is not equal to y, because I have defined my Green's functions so that x is not equal to y. Is it not? Because this is phi of y minus x. So it is defined, no, for x not equal to 0. So if x is equal to y, then it is undefined. So this is the case, and it is symmetric, means g of xy is equal to g of y of x. Okay, for all xy is in my omega and x is not equal to y. And another property is that it is positive, g of xy is positive for all xy is in my omega and x is not equal to y. Okay, one can easily check these things. So by differentiating and all these things, and g of xy is positive. So this is a little bit tricky, so I'm not going into the prove it, but other two things are somehow easy. Okay, so as I said that if u is in C2 omega solves the Poisson problem, then it has expressions like this, and also vice versa. I can say that I have a Green's functions for my domain, and ux, which is given by this form, will satisfy my problem. Okay, the Poisson problem minus Laplace u is equal to f in omega and u is equal to 0 on del omega. Okay, so now we try to find out Green's functions for some special domain, in particular for Rn plus, okay, and for the ball, unit ball. So let us find out the Green's function for Rn plus. Rn plus means basically this is all those x1 up to x of n such that my xn is positive. Okay, so this is, you see clearly it is unbounded domain. It is unbounded domain, but it is open, and the boundary is basically xn is equal to 0. Is it not? So that means what I want to find? I want to find this correction functions phi xy such that, so we want to find phi xy such that Laplace phi x of y is equal to 0 for y is in my Rn plus, and what I want that phi x of y should be P of no, y minus x for y is in my dou Rn plus, isn't it? Is on the boundary. That is actually you want to find out. So for that, what we are considering, we first consider the reflections. So now x is in fixed Rn plus, and I am considering reflections, which is x bar, reflection through the boundary, that is nothing but which is x1, x2 up to xn, xn minus 1, and then minus of xn. So now you see that this x bar, it is basically, it's not in my Rn plus, it is in the other side. Okay, so it is not in that domain, it is outside of the domain. So now if I define Px of y, which is my P of y minus x bar. Okay, so already we know that this is a P is a Laplace, the fundamental solution of your Laplace equation. So and what do we know that y goes to P of y minus x whenever y not equal to x, that is harmonic. So with respect to y, this is harmonic because x bar, it is outside of your domain. So y cannot be your x bar, is it not? So it is harmonic. So this implies my Laplace of Px of y is equal to 0 for all y's in my Rn plus. Is it not? So what I need to check then, I need to check that on the boundary, it should be P of y minus x. So for that, if I try to see that for y is in my dou Rn plus, okay, so then you check that mod of y minus x is equal to mod of y minus x bar. This is because this is your any x is in, okay, x is in here, so x bar is exactly like here. And for any y, if you consider this is in this, no, this is yn is equal to 0 there. So now we see that this length, okay, they are same actually. And what I know that this P, the fundamental solutions, we are looking for the radial solution. Since this P is radial, is it not? What I can find out that my P of y minus x, this is same as my P of y minus x bar, because P is a radial solution, is it not? We're looking at that u of x is equal to v of r for mod x is equal to r, and from there we deduce, and looking at that expressions, we define the fundamental solutions. That means my fundamental solution for Laplace equation is radial, and hence since the length y minus y minus x, length of y minus x is same as length of y minus x bar, then P of y minus x is same as P of y minus x bar. So that means what? So this one is nothing but my P x of y, no, by definitions. So that means P x y, whenever y is in my boundary of my domain Rn plus, this is P of y minus x. So hence the Green's functions for this Rn plus. So Green's functions for Rn plus is g of xy, which I want to have. This is Pxy, which I have P of y minus x bar. Is it not? Sorry, P of y minus x minus P of y minus x bar for all xy is in my Rn plus, and x is not equal to y, because by definition x should be not equal to y for g of xy, because this x bar is the inversion, sorry, not the inversion, it is basically the whatever I have defined is, no, the projection kind of things. X bar I have, you just project it from here. Okay. So these are the Green's functions for this thing. So now what I try to find out the solutions for that problem. In particular, if you look at your expression here, I need the, yes, here I need basically the doji do nu. Okay, doji do nu I need. So what is your do G do nu? Do G do nu is nothing but I can have G do G do yi dot no nu I summation over if nu is equal to nu and nu 2. So now in this case you check that do G do y of n, this should be nothing but minus 1 by n alpha n yn minus xn by x minus mod y to the power n, and then minus yn plus xn because of this minus x minus of these things x bar we have that again I can write in terms of xn, that is y minus x bar whole to the power n. Okay, so now this has the same length. So if y is in my dou Rn plus, then x minus yn means x minus y mod is same as y minus x bar n bar. So from there I have, and then if you look at the normal, in this case this is basically 0 0 0 0, and then 1 you have minus 1. So from there if you just calculate this part, what I have for y is in dou Rn plus dou G dou nu of xy, this is nothing but minus dou G dou of yn times x and y, and then you calculate this should be minus 2 xn by n alpha n. Okay, this is nothing but the ball of n times ball of 0 1, and then 1 by x minus y to the power n. Okay, you just check yourself these calculations. So now after having this, I can find out the Poisson formula for the Poisson problem on Rn plus, in the sense that if I define, so I like put as a theorem that if I consider G, which is my C of Rn minus 1 intersection L infinity of Rn minus 1, then the function defined by u of x is equal to integral over r of n minus 1, okay, k of x y gy of dy, and what is your k xy? I am defining k of xy, this should be 2xn by n alpha n, okay, and then 1 by this is xn square plus summation over I is equal to 1 to n minus 1, this is xi minus yi square whole to the power n by 2, this is my k. Then this u satisfy the following property. What I can have, that u is in C infinitive of my Rn plus intersection L infinitive of Rn plus, and second is Laplace u is equal to 0 in Rn plus, and third is that limit x goes to y when x is in my Rn plus of u of x, this is equal to g of y for each point y is in my dou Rn plus. In the other hand, it satisfies that equation because I am considering f is equal to 0. So it is minus Laplace is equal to 0 in Rn and u is equal to g on my delta of Rn. Okay, so this is called the Poisson formula for Rn plus. Okay, it is the Poisson formula, and this k is called the Poisson kernel. So in my node, actually, I made a little mistake, so I put their product, but it should be the summation sign. You just check it there, it should be the summation sign. It is just coming from just using these formulations here. Dou G dou nu, if you just look at here, no, if you just put it in this expression here, so now in this case you don't have f. Okay, so this is now dou of Rn, you can think of this is Rn, R of n minus 1, and then G of y, and then dou G dou nu, already I have wrote down there, dou G dou nu, what it is here. So from there you can find out, this is x minus y to the power n for y is in dou of Rn plus, and hence that is the expression I am writing down. So this is called the Poisson kernel for Rn plus. Okay. So now if you just consider a two-dimensional case, so what I'm saying, for example, for n is equal to 2 case, and suppose omega, which is a half plane, means x2 is positive, and now suppose my G is in CR intersection L infinity of R, okay, then the solution, which is defined by, I can think of u of no x1, x2, which should be what? This should be that kernel integral over Rn x y g of y dy. So from there, what I can write down, this is 1 by pi, because alpha of n, this is the radius, the measure of ball in this case. In this case, in this circle, unit circle. So then this is pi of r square, that means pi, and then 2 got cancel out. And then I have minus infinity to plus infinity. X2 now I have, because this is xn, x2 g of y, okay, or y of 1, and then I have x2 square plus x1 minus y1 square of d of y1. Okay, this is the expressions for these things, and now this solves the Dirichlet problem. Laplace of u is equal to 0. That is how the previous theorem says, in R2 plus, and u of x of 0, which is equal to g of x on R. Is it not? U of x of 0 is equal to g of x on R. And not only that, my u is bounded. So that is why already you put it, u c infinity Rn plus intersection u L infinity of Rn plus, means u is bounded. So why u is bounded? I can think of that u of x1 and x2 mod, this is less than equal to, if you look at, so g is bounded, so I have some constant by pi integral over r. So now from here you have your x2 is positive, x2 by x2 square plus x1 minus y1 square, and then if you change, so this one is less than equal to 1 by that x1 minus y1 square, and then if you change the variable, so then what I have, this is dy by some y square, and this one is finite, this integral. So this is less than equal to some another constant, some c tilde by pi. So the solution to this Poisson problem for n is equal to 2 case is bounded. Okay, means that there actually we have proved it for n, any arbitrary n, but here actually we have seen that using that expressions and so on, that it is also bounded. Okay, so this is using the Green's function. So if you know the Green's functions for the domain, then I can find out the that is called the Poisson representation formula for the Poisson problem. Say minus Laplace u is equal to f and u is equal to g on that domain. Okay, so let us try to find out the Green's functions for the unit ball. Ball of 0, 1. Okay, that is the unit ball. Unit ball in Rn. That means all those x is in Rn such that norm of x is less than 1. Okay, so the boundary is basically your sphere. And sphere. Okay, so for that again the same thing I can do. I can try to find out that correction function phi xy such that Laplace phi xy is equal to 0, and then whenever y is in my boundary, then it gives you phi of y minus x. Okay. So for that case, I try to define some called the inversion. So if you fix x is in my ball of 0, 1, I define my x tilde, which is x by norm of x square. So if this is my unit ball, so for any x, so it is something, it may be here, some point here. Okay, it is outside the ball actually, because if you look at that mod x, this is 1 by mod x, so that is greater than or equal to 1. Okay, so it is outside the domain. Okay. So looking at that, I am defining Px of y, which is P of mod x into y minus x tilde. Okay. I am defining Pxy and y tilde. Now again you see that it is harmonic. So Laplace y of Px of y is equal to 0. Okay, from here actually you'll see that it is actually equal to 0 for x is not equal to y. And what happened for y is in del omega? So for y belongs to dou of b of 0, 1, that means norm of y is equal to 1. So my claim is this phi x of y, it should be my phi of y minus x. Then actually we are done. Is it not? Then we are done. So why this is so? So for that case, we try to find out the following. Look at what is my mod x y minus x tilde square. So this one is nothing but, okay, so for y is in my dou b of 0, 1, that means mod y is equal to 1. I have this is mod x into, so this is mod y square minus 2y mod x plus x tilde square. Is it not? So square. So now mod y square is equal to 1. So what I can write down, this part, it is mod x square minus. So now I have y, 2y and then mod x. So what is your x tilde? X tilde is nothing but x by mod x square. So mod x square, that means I have 2y x. Okay. And then plus, so x tilde square, this is nothing but 1y x tilde square. And then I have x square. So this is nothing but 1. Okay. So now this part, again, mod y is equal to 1. So from there, I can write down this is nothing but x minus y that square. Okay, this is x square 2xy plus mod y square is equal to 1. Okay. So since this square is equal to this square, that means what I can say that the phi of mod x into y minus x tilde, this is same as, because phi is radial mod of y minus x. And since phi is radial, this is same as my phi of y minus x. Okay, so what I am having that phi of xy is equal to phi of yx whenever my y is in the boundary of ball of 0, 1. That means if y is in dou b of 0, 1, then I have phi xy is equal to phi of y minus x. So therefore, what is the Green's function? Green's functions for ball of 0, 1 is, I can have g of xy. This should be phi of y minus x minus phi of norm x into y minus x tilde. Okay, this is the Green's functions for ball. Okay, xy is in ball of 0, 1 with x is not equal to y. Okay, this is the Green's functions. Now you check that what is my dou g dou nu at xy whenever y is in my dou b of 0, 1. These things is nothing but I can write this is summation over I is equal to 1 to n. So now what is the outward normal in this case? It is nothing but y, no, because it is a sphere. Is it not? So the boundary is the sphere. So it is itself your y. If y is in the boundary, this is y. So that means it is nothing but my dou g dou yi xy dot yi. Is it not? So you try to calculate this part by yourself. This is nothing else, because already we know that it is in terms of should be phi and so on, and we have that expressions for my phi, so you can directly find out what is your dou phi dou yi and so on. And then if you just try to calculate what it should be, it turns out to be this formulation. This is minus 1 by n alpha n 1 minus mod x square by x minus y to the power n. Okay, you check this formulation. It is just coming from there. You find out this dou g dou yi and this thing, because in this case, what is the normal vector? Nu is nothing but your y. Is it not? So that I have nu I and so on. Okay. Because see, this one is nothing but get g dot nu. That means this is vector vector. So this is in a summation form and so on. Okay. So then you can look at the Poisson formula for that. U of x, I can write down. This is 1 minus mod x square by n alpha n integral over dou b of 0 1 g of y d sigma y by x minus y to the power n. Okay, so this is a Poisson formula for ball of 0 1. Okay, so u satisfy that minus or Laplace ux is equal to 0 on ball and u is equal to g on the boundary of ball. Okay, so if you solve this problem, if you define your u, then you solve this problem. Okay, that if u is in C2 B intersection C of B closure, solve this problem, then it is satisfy this equation. Okay, so now you can check by yourself. If you just look at this is ball of 0 1, I want to have same thing else for ball of 0 r. Okay, so their radius is 1. If I just try to find it ball of radius 0 r, then idea is nothing. So I can define my w of x, which is equal to some v of rx. Say x is in my ball of 0 1. Okay, and then you try to reduce this to in terms of my v, then actually you will get it. Okay, so I'm just writing down the formulations for that. So then the kernel here in this case k minus mod x k n alpha n, and then I have this part. So for ball of 0 1, the kernel should be, so this is kind of, I can think of this is integral over dou b of 0 1 k times x y g y d sigma y. This is my kernel, no, Poisson kernel. So in this case, for ball of 0 1, my Poisson kernel k xy, it should be looks like r square minus mod x square by n alpha n times r. Okay, and then I have 1 by x minus y to the power n. So r square minus mod x square n alpha n r times 1 by x minus y to the power n. So what is your x? X belongs to ball of 0 r, and y should be belongs to your dou b of 0 r. Okay, this is your Poisson kernel for ball of 0 1, and hence the solution to this problem I can write down u of x. Okay, this is integral over dou b of 0 r k of xy, or maybe I can put it kr of xy, then gy d of sigma y. Okay, so this is the Poisson expression or the Poisson formula for the Laplace equations minus Laplace u, or Laplace u is equal to 0 and u is equal to g on the del omega, and then you have this expression. Okay. Okay. So suppose the same formulations actually we can say, like I have write down the theorem for Rn plus, so I can say here also same thing else. So I just put as a theorem that let G belongs to C dou B of 0 R, then define my U of X, which is exactly same. I wrote down 0 R kr of xy gy d sigma y, then I have the following: u is harmonic in ball of 0r, that means Laplace of u is equal to 0. 2a, u is bounded. Okay, so I need see u is in continuous dou b 0r, so it is automatically it is bounded, no? Because g dou b 0r, it is a compact set, so continuous functions on a compact set is bounded, so g is always bounded. So I don't need to impose the boundedness here, because for my previous case it is on Rn minus 1, no, it is unbounded domain, so that's why you need to impose the boundedness, but here it is automatically g is bounded, so u is bounded. More precisely I can say that u x, that mod, this should be less than or equal to that g of L infinity, means some constant of g of L infinity, no? Okay, actually if you see that integral over this k x y r, it gives you 1. And third thing, that it should satisfy your boundary condition. So similarly I can think of it is in a limit sense, limit x goes to y, where x is from ball of 0r, means it is approaching, so this is your boundary point, any y, so x is from here, so it is approaching in this direction of your u of x, this should be g of y, because no, u is in continuous up to your boundary, so it is also gives you, and the boundary it is given gy, so it should be your g of y for each y gene belongs to dou b of 0r. So on the other hand, the theorem says that the solution to this problem minus Laplace u is equal to 0 on ball of 0r, u is equal to g on del omega, is given by this Poisson formula. U of x is equal to 0, and this kr is called the Poisson kernel. Okay. So using these things, actually we try to deduce something which is really important, that is called the Harnack's inequality. Okay, there are different types of Harnack's inequality, but this one is also one kind of special case of Harnack's inequality. What I try to say is the following. So let u be a positive harmonic function in ball of 0r, then r to the power n minus 2 r minus mod x by r plus mod x to the power n minus 1 u of 0 is less than equal to u of x is less than equal to, I have bounds for this, r minus 2 r plus mod x by r minus mod x to the power n minus 1 of u of 0. Okay, how to prove it? This is really important. This is called, sometimes called the Harnack's inequality. Sometimes it is called Harnack's inequality. So u is harmonic in ball of 0r. So suppose I can think of, also it is positive. So I can think of, suppose u solves my Poisson equation. Suppose u solves minus Laplace of u is equal to 0 in ball of 0r, u is equal to g on dou b of 0r. Okay, and now suppose my g is positive. Okay, so since g is positive and it is harmonic functions on ball of 0r, so by maximum principle I can say that my u is positive. Okay, so if g is positive, then u is positive by maximum principle. It is harmonic on 0r, and then u is positive. So now, since I have this thing, so what I can say that not only that, u has an explicit solution. How it is looks like? So u of x, it should be r square minus mod x square by n alpha n of r integral over dou b of 0r, and then I have gz 1 by x minus z to the power n d sigma z. So now if you look at my expression here, there is no g involved. Okay, so that means I need to substitute in some sense, so there will be no g. Okay, so let's see how one can do it. But it involves u0. So let us try to find out what is my u0. So what is u0? u0 is nothing but my r square by n alpha n r. Is it not? And integral over dou b of 0 r. This is gz by x minus x is 0. So this is mod z to the power n d sigma z. So but since z is in ball of 0 r, mod z is equal to r, so I can take out. Then this is r to the power n. So from here what I have, this one is r to the power 2 minus n and 1 by n alpha n r integral over dou b of 0 r gz d sigma z. Is it not? This one I have. So now that means I can think of 1 by n alpha n r integral over dou b of 0 r gz d sigma z. This is exactly my r to the power n minus 2 now of u of 0. Is it not? This is r to the power n minus 2 into u of 0. Okay, so this is a good expression, so we will use it. Now we try to find out that inequality form. Okay, let us try to find out the right hand side inequality. So for that, what I know that if you look at for any z is in my dou ball of 0 r, then what I can use the triangle inequality, because mod z is equal to r, so r minus mod x, this is always less than equal to mod of x minus z. Is it not? For all z is in ball of 0 r, because this is mod of z, no? Mod z is equal to r, mod z minus mod of x, and that mod is less than equal to mod of x minus z, no? The reverse triangle inequality. So using that I have this part. So now if you have these things and I have considered g is my positive, then what I know, my u of x is equal to, I can consider r of mod x times r plus mod x, because this is r square minus mod x square, n alpha n times r integral over dou b of 0 of r, and I have gz into 1 by x minus mod z to the power n d sigma z. Okay, so now this is less than equal to, since I put g is okay, so non-negative is also fine. Since g is my positive, and from here what I can write down? So this implies that 1 by x minus mod z to the power n, this should be less than equal to 1 by r minus mod x to the power n. Is it not? So now if I consider this is r minus mod x to the power n, so I have r minus mod x, so from there I have r minus r plus mod x by r minus mod x to the power n minus 1, and then I have n alpha n times r integral over dou b of 0 r, then I put gz d sigma z. So now this expression already I have, this is same as r plus mod x by r minus mod x to the power n minus 1 times r to the power n minus 2 into u of 0. Is it not? So you see this is exactly my right hand side inequality. Okay, so first inequality is proved. Now to prove the second inequality, again I can think of x minus mod z, this is less than equal to mod x plus r for all z is in my dou b of 0 of r. So now again if you do the similar calculations, so what I have, so in this case I have replaced by r minus x, so then you have to replace by mod x plus r, so what you end up with, but it is in opposite sign. So what you end up with, this should be r minus mod x, okay, by r plus mod x to the power n minus 1 r of n minus 2 times u of 0, this is less than equal to u of x. Okay, because z is positive, so there is no problem. This I have. So now if you combine that part, you will get this Harnack's inequality. Okay, so I'll use these properties of Harnack's inequality to say something that if my u is non-negative harmonic functions, say on whole R2, then u must be constant. So by using Liouville's theorem, what we have proved that any bounded harmonic functions in Rn, it is constant. Okay, so for there we are using the properties of the derivative properties of harmonic functions and so on, is it not? By using that mean value theorems and so on. So from there we have seen that the derivative is equal to 0, and since it is a Rn is connected set, so it is equal to constant everywhere. But here what I am saying that if you use non-negative harmonic functions on say R2 for simplicity, for R2, then u is also constant. How to prove it? So example, what I try to say, and then I'll stop it for this chapter. So let u be a non-negative harmonic function, say in particular in R2, then u is constant. So as I say that I don't need actually positivity, only even non-negativity is also enough for my previous proof. No, why this is so? U is harmonic in whole R2, that means also U is harmonic in ball of 0 R, it is non-negative, hence this Harnack's inequality holds. So by Harnack's inequality, what I can say that for any R is positive, I can have R minus mod x by R plus mod x of U0, because I just put n is equal to 2 in my previous result. This is less than equal to u of x is less than equal to r plus mod x by r minus mod x of u of 0. So now I can send r goes to infinity. Sending r goes to infinity, what you have? So you see that this part, because now mod x is fixed, okay, but fixed but arbitrary. So this goes to 1. So you have your u0 less than equal to u of x is less than equal to u of 0. That is that u of x is equal to u of 0 for all x is in my R2. Okay, so this implies u is constant. Okay, so I stop now. So what it says that if you have a non-negative harmonic functions on R2, okay, then it is constant. Then it is constant by using the Harnack inequality. Okay, so this finishes my Laplace equations, and then the next class I will talk about the heat equations, the properties of heat equations. There also we try to deduce the fundamental solutions and again kind of maximum principles and so on, and we'll see. Because for the heat equation the time variable is there, so you will see that whenever I am considering this omega closure, but there you have the cylindrical type of things. Okay. We'll consider from 0 to capital T time, and then omega is your omega, and then we'll see. Okay, so I'll stop now. Any question?